I'll start recording and kind of. Okay, I think we're about ready to start. Sorry to cut any conversation short. Tonight we have Phil Freeman presenting principal type schemes for functional programs. If you haven't read the paper, it should be a lot of fun. If you have read the paper, it should be even more fun. Thanks to Brainium for hosting us. Jake, I don't know if you have any words or...
Yeah, I mean, we're honored to host a group. I think it's a great concept, the book club for papers, and I'm happy to have you guys here. We are very interested in talking, I guess I should mention. And that's it.
Okay, thank you.
Okay, so I'm going to talk about this paper by Damas and Milner called Principal Type Schemes for Functional Programs. So the paper, broadly speaking, is about the Damas and Milner type system, which is one of the sort of classical type systems for functional languages, and it's been the inspiration for a lot of modern languages such as Haskell, F#, things like C# and Scala to a certain extent, Rust. So the agenda is pretty simple. I'm going to go over, I think I have 30 slides, just to go over sort of the sections of the paper, the theory and some of the results, not the proofs, and just to explain some of the notation in the paper, things like the typing judgments. And then, because the paper I think is sort of best understood, there's sort of a description of the algorithm W algorithm, in the paper, which you can just sort of translate directly into functional code, which I think is actually a better way to understand the algorithm. I've got the Haskell implementation of the algorithm that I'll just go through the end as well. Okay. So a little bit about ML. Algorithm W is was the original type assignment algorithm for ML. And ML was a functional language that originally started as the meta language for a theorem group called LCF. So you would, in order to prove things in LCF, you would actually write programs in the language ML. ML had a type, which was essentially a type of theorems, and then you would use the functional language to compose your theorems into bigger and bigger theorems, and that would be a family of valid theorems. The kind of most interesting thing about ML from a programming language theory perspective is that it had full type inference. So anything that had a valid typing derivation in any program that had a valid typing derivation in the ML type system didn't need a type annotation. You could just write the code with a type annotation, and the type would be inferred for it. But more importantly, if it had a type, it had what was called a principal type. And a principal type is the most general type for a program. So if I can give you a program and a valid type for that program, the principal type for that program is always more general, and that's the one that's inferred. So the type you thought of was a refinement of the type that I am going to infer, in other words. So I said already, ML had an influence on a lot of languages like Haskell, Rust, F#, and I consider it sort of like a sweet spot in type system design. So you can sort of push ML typing in various directions, and I'll talk about some directions that you might want to take it in later. But you sort of lose some of the benefits of the type system in doing so. So you might lose sort of decidability of typing, or you can add expressiveness, but you lose these nice properties essentially. Okay, so what does it look like? So here's a program at the top. It's a recursive program. You might sort of be able to guess what it does, but I like the name sort of abstract. I'll make it a little tricky. So we're defining f, this recursive function f, which has an argument x's. And the result is equal to, if x's is null, then nil. Else, apply the snop function to the two arguments f recursively applies to the tail of x's and the head of x's. So you might be able to sort of guess what this does if you know what these functions mean. Snop essentially is the function which takes a list and an element and adds the element onto the end of the list to give you a new list. Head gives you the first element in the list, and tail gives you everything but the first element in the list. So essentially this is a recursive definition of the reverse function. But the reason I showed this is I want you to think about, if you didn't know this was the reverse function, and you were only given these typing definitions for each of the component parts, how would you figure out what the correct type of f was, and therefore get an intuition for what f actually did? So to go through it quickly, no has this type. It says so in ML, type constructs are written on the right, which is a little confusing for me, but also read it in English. So null has the type for all a function from lists of A to Boolean. So null tells you whether a list is empty or not. So it takes a list and tells you true or false whether it's empty. Snop, I already said, takes a list and an element and returns a new list, which is the element that we on the end. Head and tail are both functions from lists of A to A for any A. So that's not right. Head has that type. Tail has type for all A, list of A to list of A. Takes everything but the head element. And nil has type list of A for every A. Nil is just the empty list. So given those, you should be able to assemble a type for f, which is a reverse function. And you can kind of put the pieces together and instantiate these A to A, B to A, you end up getting the type. Reverse takes list A to list A for all A. So that's kind of understandable, because you can kind of, if you didn't sort of recognize immediately that it was the list reverse function, you can kind of figure that out eventually and kind of put the pieces together and figure out the type. But then something like this is less obvious, right? How would you go about figuring out the type of this program? And more, how would you teach your computer to do it? That's the question that the paper solves. So this was the list example. The answer is the type is for all A, list of A to list of A. The questions we're interested in solving is just given the syntactic definition of the body of F, how can we infer the type? And what I think is a more interesting question, which the paper deals with in a section called semantics, is we kind of have this idea of what typing means for a program, but typically when you look at type system definitions, it's kind of structured in terms of proof derivations, right? So we know something has type T because I can construct a proof derivation of that, but that doesn't give us much intuition for what the actual meaning of the program is. But that doesn't tie in with our intuition of, this is a Boolean because I know it's either true or false and it can't be anything else. Or this is a function from list to list because it's made up of component parts that work with the right parts composing that way. So there's a nice piece in the paper about semantics and sort of tying in this sort of syntactic proof theory based approach to types to more what you might consider intuition. And then the final question is this idea of principal typing. So we might be able to come up with some algorithm to construct this type or give valid type for any program. But how do we know that we've come up with the most general one? That we couldn't construct a more general type for that program. Okay, so to keep things simple, the paper deals with the very restricted language, and it's essentially just lambda calculus with like bindings. So you have this type of expressions E in the paper, and E is one of 4 types of things. Okay, so E is either an identifier, so we'll just use sort of math font kind of identifiers X, Y, Z for identifiers. So you can think of those as sort of variables in your program. You can have expressions which are applications. So given 2 sub-expressions, I can apply the first expression to the second expression. And in ML and a lot of related languages, you just write that by juxtaposition with a space of the 2 terms. You can have lambda abstractions. So for the purpose of the paper and mathematical notation, you write out the lambda symbol followed by the variable you want to find, the period, followed by the body of the lambda expression. So you can think of this as introducing a function. So if I want to take the function that takes a natural number n to n plus 1, you would denote that by lambda n period n plus 1. So those are valid expressions. And the final thing is a let binding. So this, you can sort of, you can think of encoding this in terms of abstractions and applications, but in terms of typing, it's very useful to have this as a separate type of expression in language, where you want to bind a set of expression E to an identifier X, and then reuse X in multiple places in the body of a second set of expression E prime. So for example, I could say let increment equals lambda n goes to n plus 1 in some function I use it maybe multiple times or maybe never. So here's some examples, all of which are functions, I think. First one is the identity function, so just the function which takes x to itself. The second one is the function application function, so it takes two arguments x and y and returns the application x plus y. The third is the same thing, but now instead of applying x to y where x is brought into scope like lambda, f is assumed to be brought into scope somewhere in the training context. So maybe f is the increment function, and f just happens, increment just happens to be in scope because it's defined globally or brought into scope in a lambda above somewhere. And then the last one's quite interesting. So it's not immediately obvious how you can construct the typing derivation for this. But if I take this application here, x and y go to the application of x to y, and bind that to f, then I can apply f to itself. And the reason this is actually a valid typable program is that let bindings in ML get what's called let generalized. So these get polymorphic types essentially, and the two instantiations of f get different type instantiations. So even though this f has one polymorphic type, it's used at two different monomorphic types inside the body of the let binding. Okay, so that's our language for terms, and then we have a language for types as well, which is again very reduced, just to keep the problem simple. You actually have two classes of types. You have what's called monotypes and type schemes from the title of the paper. So monotypes are simple things like booleans, strings, lists, and type schemes are types that have one or more polymorphic type arguments. So monotypes are simple. You can have variables, which I'm going to write with Greek letters alpha, beta, gamma. We have a language of, a class of primitive monotypes, so things like your standard Boolean, integer, string, that you just add into the language to make it useful. But actually, they don't really turn up in the proofs of the paper very much. And then from those, you can construct function types. So given any two of those types, let's say alpha and beta, I can construct function space alpha arrow beta, which is the regular functions that we know. Feel free to stop me, by the way, if there's...
Could you go back one slide then?
Yeah.
Just a question about the bottom one.
Yeah.
Is that related to the monomorphism which we asked for?
It's related in the sense of the concept of monomorphism is the same concept, in the sense that, so this has a type that has been generalized to include like polymorphic type, that's been quantified over the polymorphic type arguments. Okay? And here we're instantiating, so some of those have been made monomorphic. In Haskell, there's restrictions when you define a function at the top level on how polymorphic it can be, and it's polymorphic in sort of the same sense that this is polymorphic. Any other questions? Okay, so those are monotypes, those are the simple types, and then you have type schemes. So type schemes are types that have been generalized over one or more polymorphic arguments. So we have two types of type schemes. We have all the monomorphic things just lifted up to the type scheme level, and we have any type scheme with a for all in front. So these are just constructed kind of inductively by taking a monotype and then shoving a bunch of for all in front. So you take, usually what would happen is you would take all the three variables, so all the variables that didn't have a binding somewhere in the type, and you would bind them all using for all at the front. And you'll see that actually in the algorithm. Okay, so we have.
I'm sorry, I wanted to ask about the for all and why is it necessary? What does that change about things?
Well, it's kind of like a very simple way of adding polymorphism to a language. So languages have like different types of polymorphism. Haskell has this type of polymorphism, but also has type classes and then you have subclass polymorphism that you see a lot more in other languages. This is sort of a different approach to polymorphism, but you get a long way with it. It's sort of simpler by comparison to subclass polymorphism, but you can do a lot with it. So, large sort of expense to weight ratio, I guess. Right, so we need this concept of substitutions. The algorithm W basically is going to work by substituting type variables whose types aren't known for known types, bit by bit as we work across the syntax of terms. So we're going to start with the kind of the leaves of the tree of the AST, the syntax tree of the term you want to type, and work up to the top. And as we go, we'll build up this mapping or substitution from variables to types. And then when we get to the top, hopefully that substitution gives us enough information to give a type to our program. So given a type scheme sigma, one important thing is that you can actually apply, so remember that a type scheme sigma was a monotype that had a bunch of bound variables. So you can think of those bound variables in the for alls as type holes, right? So I can plug types into those type holes using a substitution.
Bound variables?
I forgot what I said, but
Some kind of variable. There's a word before the word variable.
oh, bound maybe.
What is bound?
Yeah.
Bound. Got it. Great.
So you can think of them as type holes in the type expression, and you can plug the mapped types from a substitution. So if I have for all alpha, and I have a substitution which takes alpha to string, then I can instantiate the type scheme against a string. And you get simple subtyping relation using on type schemes from. Sorry, bear with me a second.
But when you say bound, you're talking about type variables bound to types.
Yes.
Okay, not bounds.
Right. All right. So instantiation under a substitution for a type scheme actually gives a subtyping relation, simple subtyping relation on type schemes, and that'll show up in the typing rules as well. Okay. So then the paper goes into this section on semantics, which I kind of interpret as how do I tie my intuition for what typing judgment really means to the kind of very rigid proof theoretic type judgment interpretation. So the way the paper does this is, and it actually splits over this paper and the previous paper, is to construct a semantic domain, which is a CPO or complete partial order, and the paper calls it V. The way you construct V is you take, so you can think of V as sort of a universe of all programs that's untyped. And there's going to be a function which takes types to subsets of V, which identify, how you delineate the types of expressions in V. So the way you construct this is to just basically take a big union of all the primitive things, add in functions just synthetically. So you just close this CTO over the function constructor, and you add in an error so that if anything goes wrong in your semantic function, you can just result to the error. And the paper, actually the previous paper that's referenced, gives this semantic function epsilon. And epsilon takes, so it's going to map into V, which is the semantic domain. It's basically going to tell us how to interpret expressions and give a value of this big universe of expressions. So epsilon takes E, which as it was our term language, and it takes a substitution for all our identifiers. So a function which takes an identifier and gives me an interpretation of V. So the semantic function says if I'm given an interpretation of all the atomic parts of an expression, then I can piece that together and give you a semantic value that represents the semantic level.
What is ID?
The sets of identifiers. So you think just strings.
And those are representing
The
terms.
identifiers in the term language.
Okay.
So I think the first thing in the term language is identifiers X, Y, Z.
Okay.
So basically, this you just get tripped up when you hit an identifier because you need to substitute it for something in V. And I think in practice in the paper, the way this works is you kind of work by mutual recursion, building this substitution of identifiers and this semantic function epsilon. But basically, this is kind of more complicated than it needs to be. It basically takes expressions, syntactic expressions, and gives us semantic values in this big universe type.
Well, I'm still confused about that second element. You got this chain of three things. The second is a function.
Yep.
What does that do?
Okay, so this is an argument which is a function. You can just think of this as a context. It maps identifiers to their semantic value. So as you work under things like lambdas and let binders, you're going to get a value assigned to an identifier, right? By a function application or let binding. And that is going to associate with that identifier a semantic value. So that builds this function here. So by passing in that function and a bigger expression, you can give a semantic value to the bigger expression.
So is there ever more than one function that could fill the role of that second item?
Well, it depends on the variables. Variables are in scope. So,
I mean, it looks like it's set up to take different. That E is an expression, right?
mm-hmm.
Epsilon takes an expression and some function. Does it always take the same function in order to figure out what the expression should map to in your semantic function? Okay.
You said it's easier to think of it like a context, so it's almost like a map of like a given context. When you have an expression, you can have it in a context, and then that to a semantic, right?
It's the context of the environment.
Yeah, exactly. So honestly, I don't have many slides on this, and I intended to sort of skip over and use it as a sort of springboard to get to sameness. But I mean,
so playing on what you're saying is what you're saying, but it's like your environment. It's a set of things you built up so far.
yeah. So the way this is going to work, I mean, for the purposes of the talk, you can just pretend this doesn't exist. You want the semantic functions give you a semantic interpretation of every syntactic expression. Yeah?
Okay.
But in reality, as you implement this function, you get into things like lambda functions and lambda expressions and let bindings. You need when you get to a variable at the bottom level, right? You need I can't just sort of like magically create a semantic value for that. So I need to have sort of accumulated it somewhere as I descended the tree, and this is the accumulator parameter that accumulates that little answer. That makes sense. Yeah. Okay. So the path to sameness is defining sameness. Is that we define this judgment with the turnstile, and confusingly, there's two turnstiles in the paper. One is semantic turnstile, one is sort of proof theoretic turnstile, and the one we're interested in right now has two rightward pointing lines. So you can read this as in the context A, B semantically has polytype sigma, I suppose. And the way so we have this semantic function epsilon, and the way to interpret this, this is interpreted with this expression at the bottom. So E has type sigma in context A if the epsilon function assigns the expression E into the subset that is identified with sigma in V in every context nu such that nu respects all of the things in A. Okay? So nu has to assign, so nu is an environment, nu is this, so nu is plays a role of this thing. Okay? Nu assigns values to identifiers. So for every such nu such that the identifiers are bounded under nu in such a way that respects A. So for every bound thing in A, nu assigns X to the corresponding subset of the I universe. If that holds for nu, then epsilon takes E to something in the right subset of the universe.
So I want to make sure I understand what you're saying there. So it's in other words, if all of the variables that are used have semantic values assigned to them in the context.
Yeah, so you have some context. So the context says things like increment has type number to number. Okay. If you give me an assignment of identifiers, increment 2 types, two subsets of V, then that has to be compatible with all the things in my context. It has to take increment to the subset that I picked for number to number. If that's true, then I can look at the right hand side. If the right hand side is true, then I determine the judgment to be.
Can you pronounce the turnstile line?
I would say something along the lines of, I'm sure there's a sort of correct way of pronouncing it, but I say under context A, we can determine semantically that B has type sigma.
So the turnstile is under the context of.
In the context, yeah. The key thing that we're going to get to is we have this semantic judgment, and the semantic judgment says that at runtime we expect B to have type sigma. It respects all of the invariants that we expect things of type sigma to have. So if it's a function type, it behaves like a function of type sigma. And then we have a proof theoretic judgment, which we're going to construct using these sequence. And the soundness results say that if we can come up with one of these proof derivations, then the semantic the semantic judgment hold, which basically means that compile time, things that are correct at compile time work well at runtime. Okay, so we've got 6 rules. And when you see Henry Milner on Wikipedia, you usually see these 6 rules. They're a little bit sort of densely packed into small space, so I'm going to go over each one a little bit in detail. So the simplest one is the variable rule. So the way these things work is we have a horizontal line. It's written in sort of sequent calculus style, where you have a horizontal line, and the horizontal line separates the things above, which are the things I'm assuming, from the things I want to prove, which are underneath the line. So this says that if this thing is true, then I can deduce this thing. Okay? And this is the sort of proof theoretic judgment, the declarative system judgment, if you like. So this says, in order to prove that in the context gamma we can deduce the excess type sigma, then it's enough. We can deduce that if excess type sigma just appears in the context. So a context is just a collection of these assignments, a substitution from variables to types, polytypes. So if the thing already exists in our context, then that's good enough. We can deduce the thing and move the judgment onto the right of the turnstile. That one please. Yeah.
So it's like if I said int x, then I know x is int.
Yeah. So the increment function was the sort of running example, right? So if I happen to know just in context, I've already determined it from some other part of my proof that increment has function of this number, then I can deduce that. That's another typing error.
So this is sort of a repetition. It's like the top is like if x is of type sigma in gamma, then the bottom is like then we know that there's an x of sigma in gamma.
Yes. So in an actual proof derivation, we're gonna construct this tree from so we're gonna start with the thing we want to prove at the bottom. Remember, the bottom thing is the goal I'm trying to get to. We're gonna have sub goals, so the tree is gonna grow upwards. You're gonna get more and more leaves appearing at the top. So what tends to happen is at the top you just have a bunch of these, and you just discharge all these obligations using this rule.
So really quick, so this is the rule that's labeled tautology in the paper, or TAUT?
Yeah, sorry, I didn't look at names. It's probably, I'm pretty sure it is, yeah. It's the only thing that sort of makes sense without it. Yeah, that's, I actually cut the LaTeX from Wikipedia, so they're also slightly different, but they mean the same things. Okay, so the next most complicated one is the application rule. So let's say we want to prove that in context gamma, the application E0 to E1 has type prime. So one way in which we can prove that is to break this, is to assume, actually, I think, aside from polymorphism, this is the only way you can proceed in this case. You know that because we've applied something, E0 has to be a function, because we have to plug E1 into the function algorithm. So the first thing we have to prove as a subgoal is that E0 is a function. So we prove that in context gamma, E0 has type prime. And then the subgoal, so then we have to have the function E1, sorry, the function argument E1 be compatible with this type, right? So the function argument E1 has to have this type tag. So if we want to prove the application has type prime, we'll prove that the function has type prime, and prove that the argument E1 has type tag. Does that make sense? Okay. And also the context will change. We can also gather new information as we move up the tree. In this case, we do. So now if we want to type a lambda term, so in context gamma, we want to we can deduce that the function lambda x goes to e has the function type prime. Well, if you think about what that means that if you assume that the function argument, that the identifier can be bound to type tag, so in the context gamma extended with the fact that x has type tag, then if those are all the case, then I can deduce that he has type tag prime. Okay, so given if I want to deduce this function as this arrow type, the only way I can do that, again, aside from polymorphism, is to assume that x has the right function argument type and then prove that the body has the result type. Make sense?
So in the previous slide, you had E being applied to something. Should I think of X as something that E is getting applied to here? Like, I don't understand at the bottom why you're talking about X fault.
Okay, so
because X doesn't appear except in that statement. There's for all X a bunch of stuff that has nothing to do with X is what it looks like.
there's no for all.
Sorry, the lamp. Oh, so sorry, I was reading the lamp.
So the reason there's an X here is because terms are defined by induction syntactically, right? And one of the constructors for a term is lambda xe. So I have to I want to be able to say how I move up the tree if I see one of those things. So if I see lambda xe has type, and the type better be a function because it's the only thing this could possibly have as its type, then I can move this. If I can assume x has type term, move that into my context, and prove that the body has the right thing, then I'm good.
Yeah.
That answer your question? Sorry.
Yeah.
Okay.
I'm actually a little hung up on the distinction between assuming that x has type tau and proving that, like, what's the, so, like, if you're trying to prove the bottom, then you sort of know that it's like feeding an input to the top that x is of type tau, and then you have to prove the thing on the right. It's sort of a strange
So there's no kind of, so this is called the declarative system because I'm just kind of like building up the axioms that like the axioms that make up a valid judgment, a valid deduction of judgment. There will be, when you say like inputs, you can think of, there's an algorithmic system, and that's what algorithm W defines. And then you sort of think of this as like information being questioned, around the system and inputs and things like that. But this is just sort of purely syntactic manipulations at this point.
I think it actually makes sense now.
So what were you saying? You confused between?
So it's just sort of interesting that I was just trying to understand the distinction between, on the left you're saying if you assume that, on the right the x and t are saying you assume that, on the right you're saying you prove that. But I was thinking at the top of the bar everything we had to prove. But it's sort of like given that x equal, given that you're in the context of whatever context you're in plus x having t, then prove that this, and then the result, that would prove the thing on the bottom.
Yeah, so you don't think of this as implication, right? This is just, the whole thing is a judgment, and there's a family of judgments, and we have rules for how we can derive judgments from other judgments. So think of this as a unit, right? So in context of this, I can deduce that. So the context defines names variable, names types. In that context, I can deduce that this has types. And then I define these rules for these things together. The way we're going to actually use this is to try and turn this system into an algorithmic system, that's algorithm W, and then prove that if algorithm W succeeds, then there's a valid deduction that's made out of these rules. Okay.
I just want to make sure I'm understanding this real quick. So it's like, on the bottom, it's like we're digging into the scope of the lambda, and then that's the result of the top. Is that kind of the way to think about it? Like we're adding the x type to the gamma environment. And now in that context, E has type tau prime because in the outer context.
Right. So I think it's probably good to think about it in terms of examples as well, right? So let's say this is the thing I want to prove, and this is the subgoal I have to prove in order to for that to be true. So suppose I want to prove that, let's say, lambda x goes to x has type int to int, let's say. Okay. Then it suffices to prove that in the same context augmented with x has type int, then x has type int. And I use the variable rule and I'm done. Any more questions on that?
So this is like proof of the abstraction. It's all the abstraction. So
What's the basic call it? I think it's much the same.
it's abs.
Yeah, absolutely.
So it's proving the idea that we can abstract to language.
So,
Language.
I prefer to obviously there's sort of an intuition here for like, this is how we expect the functions to behave. But I like to think of this as just sort of like, these are just sort of atoms of our Greek language, and then we build them up using these rules. And they don't have any direct meaning. The meaning is assigned to them by the semester. Although I don't know, there might be more to it. I don't tend to read into it like that.
Is this proving something, or is this establishing a rule?
This is an axiomatic proof system. We're interested.
So this isn't a proof of something. It is.
This is taking an industrial. Yeah, this is taking axiomatic declaration. So it might be possible to prove it for a given semantic function. That this holds, and certainly by the second term we expect that to be the case. But for the purpose of this judgment, this is just an axiom, and we're going to build deductions out of these axioms. So the paper has one. Anybody has the paper? It's at the bottom of the page that has section 5 starting on it, and it goes on to the page after it. So you'll see that you have one of these things that I want to prove at the bottom, one of these judgments at the bottom, and then we build up this tree. So it actually splits over 2 pages, which is very hard. Build up this tree, and at the top you end up with leaves, which you can just discharge with the tautology reduction.
So a way to think of it would be almost like you're solving algebra, where you can subtract the same value from both sides of the equation and it's still true. So the bottom is the expression and the top shows what would happen if you subtracted x from both sides or something.
Yeah.
So you go from a true thing to a true thing, and you keep simplifying it until you get all these tautologies on the top and you're done.
Yeah, so there's sort of 2 senses in which it's actually really similar to that. So you look at the thing that you have to prove, and this is pretty abstract, but in reality, when you actually see a concrete thing, there's usually only one rule that applies, right? So you apply that rule, and maybe if there's polymorphism involved or something, you have to pick which things to instantiate, and then you have a choice of 2 rules. But usually, it's not too bad to find the right one, and you just sort of work up. And just in the same sense that in algebra, you have these rules. I can add the same terms to both sides of an equality or an inequality, or turn the inequality sign around, or whatever it happens to be. You have this sort of set of rules, and you just do the thing that's most obvious, and sometimes you have to backtrack because you did the wrong thing. And the second sense in which it's like high school algebra is is like sort of symbolic manipulation in algebra. Is that you can actually solve these things. You can solve these things by if you learn the substitution rule for solving sets of linear equations. You rearrange the first equation, right? So that one of the variables is is equal to some linear thing, and then you substitute that linear thing. You substitute that variable for all the other things, and you eliminate it. So you can actually solve these things the same way. I was going to briefly cover this at the end, which is kind of an alternative to algorithm W, which is you look at the type. So let's say it's the type in the example, right? And then you have a binding of a lambda abstraction. You have some applications. Each one of those determines a little bit of local information. So you get, let's say, you think of it as like a linear equation, but it's an equation in type language, right? You can sort of do some rearrangements and express them do the same sort of thing where you can substitute type expressions into other type expressions, and build a substitution that way. So in a sense, you're kind of doing that here in the algorithmic system. But like I say, it's possible to try and think of the declarative system as just defining a proof system, what it means to be a valid type of judgment.
So in the algorithm W, the algorithm sometimes does need to backtrack.
No, algorithm W doesn't. I'll get into algorithm W, and I'll sort of talk about how it's defined. How you can think about it in terms of constraint solving, but it doesn't. As it turns out, I always pick one rule.
Move forward.
Yeah. Okay. I think there's only two or three more. The let rule looks a little bit like a hybrid of the abstraction and the application rules. So same thing applies. I want to prove this thing on the bottom. In context gamma, this let binding has type. So let x equals e1, e0 in the body e1 has type tau. If I can prove e1 has type tau, assuming that x has type sigma and e0 has type sigma. So if you look at this, if I give e0 type sigma, then x is bound to something of type sigma. I can substitute that into e1, so you can think of this as sort of like the pre-generated boundary substitution. Then, given that x is sigma, then inside e1, the whole, x appears inside e1, it makes e1 have type tau. Pretty quick, but questions on that one?
So this is just saying that, like, when you're doing let binding, everything, all your types have to match up, right?
Right. So when I said, this idea of like a linear equation, the analog of linear equation, so you can see this thing popping up where you have this local information appearing, right? So, I said, so in the abstraction case, the local information was, I had an abstraction, so I know a function had to appear somewhere. You saw a function, right? So that was like a little bit of local information, but there is a function and it's related to these variables, and you get these type equalities. But they're local type equalities. You need to assemble it into a global solution. Same thing here. So x has type sigma. Here's the context of E0 has type sigma appears here. We're getting sort of local information about E0 and then local information about E1, and then hopefully we can build it up into algorithmically into a global solution. But again, proof theoretically, it's just, hopefully it has some intuition in terms of soundness, but it's just sort of a judgment of what it means to type a let binding. All right, the instantiation rule. So we said that there's a subtyping relation derived from instantiation type schemas. So we're given two type schemas, sigma and sigma prime. If sigma prime is a subtype of, i.e., you can instantiate some of the type variables in sigma with monotypes, and get a subtype, subschema, if you like, of sigma. Then any term E that has type sigma prime also has type. I have a corresponding derivation of sigma because sigma is more general. Okay. Everything that has type, so this is, you can read this as like it is a relationship of subtypes. Everything that has type sigma prime also has type sigma. And the subtype relation, just to make it a bit more concrete, so int to int, the function, is a subtype of for all a to a, because I instantiated a at int. So it's more specific.
And that's where your partial order structure comes from?
Yeah, so this is, you think of this as like a subtype of relation. You get a subtype of relation or partial ordering from instantiation of type variables in schemas.
Yeah, the paper lists that is greater than.
Yeah. That's type instantiation in section 3. Right? Sorry, yeah, the rule name for that one is right, it's for instantiation, yeah.
So greater means more general?
Yes. Again, I took it from Wikipedia, so.
Yeah, the paper is showing the sigma on the top is greater than the sigma on the bottom.
Oh, okay, yeah, so it might be the other way around in the paper. But you have a relation and the proof, the judgments respect the ordering, essentially. Okay, then you have the opposite of instantiation, so generalization. So if I have, if I can prove something has a monotype, how can I prove it has a more general polynomial type? So if I want to prove in context gamma that he has type, the polymorphic type for all alpha sigma, then it's enough to prove that he has type sigma, or I just forget about the alpha, assuming that alpha is not free in gamma. So there can be no assumptions about alpha inside gamma. So you can think about that in terms of alpha has to be essentially, there can be no information. There can be no information appearing about alpha inside gamma. It's fresh. I haven't seen it before. I can't assume anything later. Does that make sense?
So alpha would be a type variable.
Yes.
And E would be an expression involving alpha.
No, he is at the term.
Is it?
So let's say let's say I want to prove the identity function, so it has type in the empty context for all alpha and alpha. Okay. Then it's enough to prove that it has type alpha in any context where alpha doesn't exist. Sorry. It has type alpha to alpha in any context where alpha doesn't exist. So alpha has to be unbound. I can't assume anything about alpha. Because so if I had something in here that said alpha was integer, then I can I can't derive, if alpha is integer, I can't derive that has this type. It's too specific.
Is that like a way of creating more general, more abstract types in some sense?
Yeah, so you can think of it as sort of like a means of like abstraction of the type level. You can sort of create interesting terms that have polymorphic types, I suppose.
So E is an expression, one of the elements of which has type alpha?
E is a term, so E is something like lambda x goes to x. And I'm trying to prove that in this context E has some type and the type is polymorphic. So lambda x goes to x has type for all alpha to alpha, let's say.
So alpha is a type of something in E.
Alpha is a type variable.
That describes some sub-expression of E, right?
I suppose, yeah. So alpha is going to appear in sigma. So you can think about it like, the x in lambda x. If that's what E is, that has type alpha. Sure.
So this is all static, right? You said as long as alpha is not free.
Right.
But there's no case where it becomes free later, or you have to backtrack or anything like that. Because this is all. I don't have a sense of the environment where this is happening yet.
This actually, when you sort of write algorithm W down, it's kind of not immediately obvious how this sort of translates into the generalization that happens. Maybe I wouldn't worry about it too much for now. Just think about this instead of saying that alpha appears abstractly. Can't find any information in the context, and then you can generalize, and you'll see where the generalization happens in algorithm W. You can see that this kind of holds.
So is this sort of the thing that says if I say here's an abstract variable x in my program, and then I say and I try and pass it into something that expects an integer, it's like, okay, fine, x is an integer. And if I try and pass it into something that says a string, it's like, wait a second, you already said it was an integer. It's not free anymore.
Right. True. So there's two aspects, I guess, what you just said, and then let's say I want to prove lambda x is type for all alpha to alpha, that's fine. If it was, let's say, lambda n goes to n plus 1, I can prove that as type into int, but I can't prove that as type for all alpha. I can't generalize that to alpha because I already have contextual information about alpha, which is that is an integer. Somewhere in the proof derivation below, I'll assume that alpha has type.
So we're working from the leaves up.
Sorry, not true. Sorry. If I'm working from the bottom up, I can try that, but then either alpha isn't free already, or like something contradictory is going to happen at the top and I'll backtrack. So this is one of those cases where if you just try and this is one of the rules where if you just try and sort of send this directly into an algorithmic system, then it's not obvious if you can apply this rule or you might have to backtrack. You might have to terminate, which is kind of why you get algorithm to be. Missing something. Anyway, Sanders says the two judgments interact nicely. So this should be the proof theoretic judgment. Turns out it's in the right pointing line. So if there is a proof derivation in the context A that E has type sigma, so I have this tree using the rules we just went over. If that's true, then semantically the same thing holds, i.e. things like indeterminate statically using proof derivations behave nicely at runtime. So static behavior determines dynamic activity. Kind of intuition I have for this. Does that make sense? So the proof of this is, I'm going to go over it, but these deductions were just derived in terms of those 6 rules, defined in terms of those 6 rules, and they're trees of sort of valid combinations of those 6 rules. So you can basically just prove this by deduction on the height of the tree. And you just sort of do it by structural deduction on the tree, on the proof tree. So you can do it for leaves, and then you do it for abstractions, you do it for applications, etc. Okay, I was going to go over the deduction and the whiteboard and combine these things together, but so I went into quite a lot of detail. Hopefully, you'll be able to sort of see roughly which rule corresponds to which of the 6 rules you would actually apply at each stage. So here's a good example of why this doesn't directly translate into a good algorithmic approach. There are 2 rules that apply here. Okay? So that's true. Okay, so we have the application rule. So the abstraction rule. The abstraction rule, I guess, doesn't apply actually, because in order to apply the abstraction rule to derive a type for a lambda term, you have to have a monotype on the right, an arrow type, but we have a polytype. So the only thing that can apply, I think, is the generalization. So the first thing we do is we degeneralize. We take all of the things that weren't free and we instantiate them, move them into the context. So essentially just think of that as chop off the alpha and beta here and remove assume they got here in the context. Then the next thing is we have an application. So we can use the application rule, twice. And then I think at that point, you might be done. You can just discharge all of the tautology with the tautology rule. You might like to go through this. This is another good example of a paper where they go through something that I think uses all 6 rules. But it's kind of interesting to kind of work through these and try and come up with a proof derivation. Okay, so that was the declarative system. And algorithm W is the algorithmic implementation of this. So how do you turn these? We said that many of the rules, it might not be obvious which one to apply or how to apply it. So this doesn't translate immediately, obviously, into an algorithm. So W is an implementation of this. And the theorem at the end is going to say, if W succeeds, then there's a proof of derivation that proves that the term you started with has the type you said it did, that W said it did. So W is a function of this type. Takes things in our expression language, so those things E that are appearing in our proof deductions, and an environment which is a substitution. And returns a new environment, so we're going to build up this substitution as we go, and returns a type for the expression. So you can, if you're familiar with Haskell, you can think of this as a function from expressions and types in the same moment. You're building a type for an expression, but you have a substitution that you're threading through and building up as you go.
Should I think of the environment as a dictionary?
Yes, it's a mapping from type variables to types. So again, it's interesting that we're building local information. All the local information goes into the substitution. By the time you get to the top of the term in syntax, then you kind of hope that all of that local information is enough and it's combined in the right way to give you a global answer to what is the type of the thing it starts with. Okay. So what I just said, W attempts to build a substitution bottom up. With this local information, we build up a bigger and bigger substitution. Hopefully it has all the information we need at the end. But you can also combine things in inconsistent ways. So I can have bits of local information that contradict each other. So W can fail. So this, the type here, if you think of this in sort of a purely functional way, this should be sort of like a means to error out here. But in my Haskell implementation, I'm just going to use the error function to just shortcut. But W can fail. And the intuition is that W is doing two things. It's collecting constraints and then it's solving them. But in reality, what's actually happening is it's doing a fusion of those two things. So you can think of the process as, so if you're familiar with this idea called deforestation, functional programming, you have a function that's defined in two parts. The first part builds up a tree of some kind, and the second part folds over the tree and collapses it down to a final answer. But you can do what's called deforesting and remove the intermediate tree by fusing together intermediate bits of the computations when you compose the two functions. So in a certain sense, you can think of this is sort of like a nice intuitive way to implement algorithms, implement these rules, but it's kind of inefficient because you have to build this giant collection of local assumptions and then solve them by that method I described with the substitution like linear algebra. So if you can fuse these things and deforest that enormous collection, then you end up with something that looks a little bit like algorithm W. And I'm going to go over the code in a second. Because I think that's kind of the best way to see how the algorithm works. With just a couple of kind of preliminary things. So there's a central notion in algorithm W called unification. So it's an algorithm called Robinson unification for solving, and it relates again to the kind of solving local information using this idea of like linear algebra, solving groups of linear equations. So if we have some first order term language and we want to so Robinson unification gives us a way to assert the equality of two terms in our first order term language and break it down into the minimum amount of information that we need for those things to be equal. So the term language the language we're talking about in this case is types. So we want to assert type equalities and break that down into smaller type equalities that give us only what we need to stick into our substitution. Again, unification collects local information. This is where this local information comes from. I see things like functions, and I collect a small piece of local information about the function, stick that information that I get out of unification into my substitution and build that up. And hopefully I can assemble a global solution for that. Okay, so just as a very brief example. Let's say I have two types, and I know based on, like, let's say an application in two terms, that these two things can be equal as types. So I unify them and say type 1 is alpha to beta function, and type 2 is the function from function beta to gamma to gamma. And I can unify these things syntactically. So I say both of them are functions. Okay, so there's a function arrow here and there's a function arrow here. So I unify the things on the left and I unify the things on the right, and I get these two equations. So if the lefts are equal, then alpha, which is the left here, is equal to the left here, which is beta to gamma.
Sorry, is that turtle symbol? Does that mean
you write unification that way. You can think of it as just equality. Equality modulo sort of instantiation of type variables.
alpha, beta, gamma, all types?
Yes. Yep. So yeah, I'm breaking these breaking these down into smaller type equalities. So it starts with this one large type equality, and I break it down because they're both functions. Take the left and the right hand with two smaller ones. So alpha is equivalent to beta to gamma, because those are the left hand side, and the right hand side is beta and gamma, so they have to be equivalent to. And then I can substitute, so again, come back to this solving linear systems of equations. If you kind of do this, if you had this system of first order equations in high school, you just sort of like substituted them in, you'd be able to take beta equals gamma and just substitute it in here and get your solution alpha is gamma to gamma. So you get this local information by unification, you piece it together, and you figure out that alpha to beta is actually gamma to gamma parenthesized to gamma. That's your global solution. So unification is kind of like the building block. But it doesn't always work. One way in which it can fail is at this step called the Kerr's check. So let's say you have the term lambda f goes to f applied to itself. So if you try and think, if you use unification to sort of piece together local information, you get this type called alpha has to be equal to alpha to beta. And you do the substitution thing and you end up with this infinite type. So the Kerr's check says that whenever I see alpha is equal to beta, if alpha actually appears in beta somewhere, then any attempt to solve that is going to lead to an infinite term. So we error out and we say that the first check failed. So here W just fails and says the first check failed. Okay, soundness for W says that if W succeeds given an input context A and gives you an output context S and the type for E that's tau, then again it's not typeset correctly, but then in context A I can determine that ES type tau.
Can you read the statement after the if again?
Yeah, if W, so remember W can error out, but if it succeeds, given an input context A and a term E, an expression E, and it succeeds with a pair of substitution S, which is the output context, the substitution that I built up, and it gives the type tau for E. So algorithmically I've proven that ES type tau. But what does that mean? It means that if that's true, there's actually a proof of deduction using those 6 algorithms. 6 axioms, sorry, that E has type tau.
So A and S are the same kind of thing?
Yes, input context, output context, or substitution. So your 2 soundness rules say you can go from W to proof deductions, and then you can go from proof deductions to semantics. So if W says that E is okay and has type tau, then E behaves like tau at runtime. So algorithm W constructs type of judgments. Another way to detect it. Questions on that?
Is that the single block turn?
Yeah, that's the one that one types like the single block proof theoretic. And then you have a kind of a converse, a partial converse, I think, to soundness, which is the other way. If you can construct a proof judgment in context A for ES for Z sigma, then W will succeed, and it will construct the type of judgment. It'll construct the type tau, but it won't necessarily construct sigma. Sigma will be more general. The type, the other way around, I'm sorry. W will construct the most general thing. So if you can give me any valid typing judgment for E, then W will give you a typing judgment, but it'll be more general than the one you thought of, or the one you thought of. And you can think of that as saying algorithm W because that constructs principal types.
What would be the most general or just general?
Well, you could have thought of the most general, but you might have thought of, so let's say, so I have a proof derivation for lambda x goes to x as type int to int. So W doesn't construct that type, it constructs for all alpha, alpha to alpha. It's more general, but this is a substitution instance is the one that W gives you.
So in that case, you described that that sounds like it would be the most general.
Yeah, W constructs the most.
It does, okay.
Yeah. Okay, so that's it for the slides. Sorry, I don't know how much. What do you want to do for? I can sort of skip over it, but okay. Further reading. So if you want to see more type systems, so I said ML has this kind of a sweet spot in the sort of like type system implementation ecosystem, but there's more interesting things you can do and add to this system. So system F and system F omega, Rankin types and type clusters, if you're familiar with Haskell, are 2 more powerful forms of polymorphism than just this Rankin polymorphism with for all that we went through. And then things like dependent types and refinement types are things that you can add to the system. But I think all of these, higher kind of types is one kind of stuff. But apart from higher kind of types, all of these have the property that you kind of lose some nice property of the system from the ML types. You move from ML to those. Usually decidability and type inference. So there's a trade-off between expressiveness in type system design and the nice properties you have with that type system. And there's some kind of newer approaches because the way algorithm W works doesn't necessarily generalize to all of these things. There's a couple of new approaches that you can apply. So I already talked about constraints, where instead of deforesting the intermediate set of constraints, you really do split the algorithm into 2 steps. You do constraint generation and you do constraint solving. SMT is like that on steroids, where you generate constraints in some. So SMT is useful for things like refinement types. So you want to actually write down kind of expressions. You know, instead of just saying this takes int to int, it might take positive int to positive int. So it takes the property n greater than 0 to n greater than 0. So if I'm working in this richer language, I can gather these constraints, and if I can't do it by first order constraint solving, then I can just pass it to an SMT solver, and hopefully it gets solved. So that's one way of doing type checking with more expression systems. And then the other is bidirectional type checking, which is one of my favorite areas. So once you realize that these things have become undecidable for type input, you realize that for certain things you're going to need type annotations. In ML, you never need a type annotation because the theory is simple enough that you can always figure out the type from the syntax. But once you lose decidability, you have to have the type annotation somewhere. And then once you have type annotations, there's not much point inferring any types anymore. If you have a type annotation, why not just check the term has a type? It's much easier often to check that something has a type that's already given to you than it is to get a type and synthesize a type from just syntax. So what bidirectional type checking does is where we have one judgment, which is the return style, we separate it into two judgments. So we have a synthesis judgment, which synthesizes types from terms when you don't have a type annotation. And you have a checking judgment, which, given a type and a term, checks that the type has that type. Given a type and a term, it checks that the term has that type in some context. And the way bidirectional type checkers usually work is that they can move between the two modes, essentially implementing the two judgments, depending on the type of the type of term you get.
That's like what OCaml does with their optional
GADT,
type checking.
Yeah.
Or, I mean, they have optional type annotations, and so
I think it's kind of cropping up in a lot of places, but I think it's a nice. Whenever you run into this problem of like, I can no longer just infer types all the time. It's a nice place. It's a nice thing to try. Right? It's usually tends to be a solution because you're going to have to have type annotations anyway. Once you have type annotations, it's sort of logical to separate the judgments into checking and synthesis. So yeah, you see it in a lot of places. PostScript uses it for its ranking type implementation, for example. You can use it for intersection types, union types, I think optional types, also stuff.
So is it different from what Haskell does? From what I know, Haskell infers everything and then checks what you wrote. It tells you if you were wrong or not.
So for Haskell 98, I don't think you need. I think you can get by with variant of algorithm W, although I might be wrong. Type classes are kind of the one thing. So there's a nice paper called Typing Haskell in Haskell, which basically goes through all of this stuff, but for Haskell 98. So that's what we're looking at. Once you start adding all the extensions like GABT and type families, it starts getting a bit more into the bidirectional area. I think the current algorithm is called Outside In, that implements GADT, type families, all this kind of stuff. We used to have the bidirectional checker, and I think Outside In is bidirectional, but I don't know too much about it, obviously. I don't know about time. I can go over the code. I can just give the link, or if people are interested, go over it. Feel free to tell me to shut up.
Okay, cool.
Yeah. All right. Well,
we'll read the crap.
I have a couple of questions if there's a Q&A session.
Yeah. Sure. But, well, I guess I'll get through this, but just get it done and then do questions. Okay, so here's a Haskell implementation of algorithm W, I think. And it's easier to see in the code. So if you're not familiar with Haskell, I tried to keep this sort of as simple as possible. And hopefully, given the ML primer that I just went over for the actual slides, hopefully it should be enough. So the first bit is we have to define the data type terms, and the paper tells us exactly how to do it. The nice thing about the paper is it pretty much directly gets translated into code. So here's our term language. Mine's labeled by integers, and I made the assumption that as you move outwards in the term, the outermost thing has the biggest integer value binder. So that's nice because it allows us to lazily generate binder names and use a sort of syntactic sugar that I'll show in a second. But the data type of expression is here. So it's a sum type. So anyone not familiar with sum types? In some other language? Okay, cool. So it's defined as one of these four things. An expression is either a variable or an identifier, and that's constructed with a binder, which is an integer. Or it's an application of two expressions, or it's a lambda term that binds this binder and has a bloody expression, or it's a let binding, and a let binding binds the binder to a name, which is another expression, and has a body. Is that? Yep. No. Okay, so I just introduced this bit of syntactic sugar. The implementations are very important, but it turned out to be convenient to, instead of writing the lamb constructor everywhere, it's nice to actually be able to use Haskell functions to create functions in my expression language. So lamb with a lowercase m takes a function, Haskell function from expressions to expressions, and it turns that into a lambda expression. And when I said this, there was a paper that was at ICMP a couple of years ago, I think, that kind of described this really neat technique using laziness to kind of guess the next fresh name. So you can pick B lazily, which is kind of neat. But it gives us this kind of higher order abstract syntax. You can see at the bottom here, instead of having to write capital lamb coming up with my bind is like 1 and 2 here, I can just write lamb. The function x goes to middle lambda, y goes to x applied to y. Has introduced this fixed double dollar for application. This is the module loaded into GHCI, which is the interactive mode. So I implemented W, takes expressions to types, general type. And I introduced, so let's do the identity function. Using the syntactic sugar, and just use a regular old Haskell function, x to x, wrapped with this lamb function. And W tells us that the most general type of that is for all A to A. Just ignore the B's, sorry, it's the prescription in Haskell can't be so coerced enough to do all this stuff. So let's do the constant function. So now if I find two variables, right? So lambda x y goes to x, I just ignore y. And that has type for all A, B, A to B to A. So I take two function arguments, they can be different types, and I return the first one. But it's polymorphic in both. We got a ready for lambda calculus expression?
Can we try one that doesn't work?
Yeah. So let's do self-application. So double dollar was the syntactic sugar for application. That was the occurs check, right? They were trying to construct an infinite type.
What does that mean, occurs check?
Remember we had that check for infinite types, and the problem was you get this local equality, so you have alpha is equal to
I
beta.
remember the infinite expression, that's right, but why is it called an occurs check?
Because the way the check works is if you have an equality alpha equals beta, if alpha occurs inside the body of beta, then it's a problem. Alright, go back to the code.
Is that what that always means? Is that what that
Occurs checks?
I've gotten occurs checks all through my life.
Yeah, that's what it means. It applies generally to kind of like first order constraint solving.
For all cases.
Oh yeah. Alright, so we have our terms, then here's the type definition. So exactly the same thing, just define it as a sum type. We have a language for primitive things, we just use strings, but I actually don't end up using them. The interesting ones are type variables, which are given binders, function, type, which is a type to a type, and I just use the syntax arrow as the constructor. And then just for convenience, the paper distinguishes between schemes and monotypes, but I just roll them into the same sum type. So this is the type scheme with these binders universally quantified, and this is the monotype that sits inside it. But here are the monotypes, first three, and then this is type schemes. Questions on that?
Sorry, can you define universally quantified? What that means? What a
Oh
bind
yeah,
is?
sorry. So the interpretation of x, b, t is for all, and then the list of things in the binders, b's, t. So,
Oh.
Yeah. So x, let's say 1, 2, 3. I don't know, 1 to 2 to 3 is for all a, b, c, a to b's. Okay, so then the next bit of the paper was substitutions. So substitutions were mappings from binders to types, polytypes. So here we just use the types within them, and I'm going to use an association list. So it's an association of binders and types. So Haskell has a function lookup that you need to look up the binder in a substitution. And you need to be able to apply a substitution to a type. So that's what this apply function does. It takes a substitution of a type and gives you a new type back. You just do it by structural induction. So the only interesting case is we have an arrow function type, and then you just basically recur on the two sides of the function type. And you need a way to combine substitutions. So that's this combine function. So given a substitution, I need the substitution that combines all of the information from both. So if I call it S1 and S2, I can take all the stuff in S1, but I also need all the stuff in S2 with all the binders replaced by applying S1. So you can do this either way around, I think, but just pick it this way.
Does everybody know list functions in Haskell?
Oh, sorry, maybe not. Yeah, do tell me if I'm like going on this too quickly if you have questions. This if you're familiar with list comprehensions and things like, I guess, Scala, Python, a few others, we're collecting terms out of lists on the right-hand side of the pipe. So given that a substitution is just an association list, so given an association pair in the association list S2, then I can, this is essentially equivalent to a map, it's just a little easier to read for me at least. So given the association from the binder B to the type type in S2, then I now associate B to the same type but with S1 binder type instead. Yeah, please do stop me. So I'm going to get through this in one more time. Alright, so unification, this is a Robinson unification algorithm for sort of collecting this local information that we want to piece together. It's just defined by zipping. So if you think about lists, if you're familiar with the zip operation from any functional language, you start at the head, the two heads, and you apply some functions to them, and you move on to the next two and apply some functions there, and you recur on the tails simultaneously. When we implement unification, we can do the same thing with the types. So we start at the top of the two types, and let's say they're both function arrows. So we do that thing that we did before, where we look at the two left-hand sides and we zip their left-hand sides. And we look at the right-hand sides and we unify those, and we zip them right. Or if we get two primitive types, then hopefully the same. So notice here, most of these cases are defined in where all things look the same. So if I want to unify the function T1 to T2 with the function T3 to T4, that's the same thing as combining these two substitutions that I get from unifying the left-hand sides and unifying the right-hand sides. I can only unify two primitive things if they're the same primitive thing. And a variable unifies with everything, except for when the occurs check fails, which is when the variable occurs on the right-hand side. And the occurs check is here, it's just to get structural reduction. It's simple. So you just go through and look through the tree and see if you can find the binder anywhere. And if it is, then you have an infinite type and fail. Questions on that? Alright, so type instantiation. So let's say I have a type scheme, and type schemes were given by S. And they need to give this fresh name supply range. But given a fresh name supply and the type scheme, we can go through and it's just an ugly recursion, unfortunately, but it goes through and keeps pulling off names from the fresh name supply and instantiating the universally quantified type variables in the type scheme with the fresh names. So this was the case where I had a type like, this is basically a set that I need in algorithm W. If I have let's have a polytype for all alpha to alpha, and I want to apply it to the int 2, let's say, then I can't apply it directly because 2 doesn't have type alpha, alpha is abstract, but I can instantiate the type. No, right now. So you can't apply it to 2 directly because it has the wrong type. 2 doesn't have type alpha, alpha is abstract, but you can instantiate the type from alpha to int, and then you can apply because 2 has type int. So here we're just going through and taking all those alphas off the front and instantiating them with fresh types. Remember, in unification, fresh types unify with everything. So here you see how we're taking these sort of steps and combining them. So like to get the right proof deduction for the thing I just said, where we apply the polymorphic identity function to 2. First we instantiate, and then we're going to end up doing unification, and we're going to unify int with the fresh variable that comes after the instantiation. So I guess there's something I maybe missed. There's this notion of unification variables. So given any type, given any sort of given any type, you can augment it with unification variables and get something that you can do constraint solving over. So in our case, our type was, we're interested in doing constraint solving over the type of types. The unification variables are the binders here, bound by B. Unification, when it sees a unification variable, it will unify it with by instantiating it, sticking that by equating the unification variable B with the other thing, sigma, and sticking that into the substitution. So this is how we do that. Gathering the local information. What instantiation does is to replace all of the universally bound things with unification variables, so they are free to be unified with other things to become more, to become less polymorphic. Generalization is a bit simpler to explain. Sorry. So this was the case where we had a monotype and we wanted to get a polytype for it, and we said that if alpha was free. If we wanted to prove that term had a polymorphic type for all alpha tau, then alpha had to be not in the free variable set, alpha context over. So algorithmically what we do is, once we already have a type, so algorithm W is going to produce some type, and there's going to be some unification variables left over. The free variables correspond to the leftover unification variables, and we can just quantify over all those unification variables. So in this context, given this monotype tau, I can generalize, I can generalize tau to the type scheme where I quantify over this free set here, and the monotype inside is still just tau, and the free set is the free variables appearing in the type minus all the things bound by the context. So this you can think of as all the things I don't have information about in the context, but they're still sort of polymorphic as a unification variable appearing in my solution. So free variables just goes through and collects all of the binders that appear inside the type. So it might be that algorithm W generates the monotype, let's say alpha to alpha for the identity function. Then I can generalize that to for all alpha to alpha, and that's the most general solution that algorithm W can do. This function that does that generalization. Okay, so here's algorithm W to talk about. So as I said in the slide, we proceed bottom up over the syntax of terms. It means we look at the leaves of the tree of the syntax tree of the term, and we gather local information there, and then we work our way up to the root. And I said that the type of W was took a substitution in an expression and gave you a new substitution, and a type. But I also need actually a fresh name supply. So I think when this was implemented in ML, this just uses a raw reference, but it has to have to sort of thread this name supply through this pure language. So the fresh name supply would need that instantiation step. So I need fresh unification variables to stick in to the when I instantiate type scheme. Okay, so W is defined using this alpha function Go. And Go is going to solve for a monotype. And then the last thing I'm going to do, once I've called Go, is just generalize the monotype I get back. So I'm going to take all those leftover unification variables and just quantify with them. That's my type scheme for the program. The more interesting thing is Go, which is the thing that constructs a monotype. So I think 6 of these, or maybe 5. 1, 2, that's 4. Oh, sorry, one of them is the generalization rule. Most of these correspond in some way to, if not exactly, a combination of one of the 6 rules in the paper for the proof theoretic judgment. Okay, so for each of these cases, we have a fresh variable, or you can, to a certain extent, just ignore the fresh variable supply and just think of it as this supply of names that gets thrown into the program. You have substitution that goes in, you have an expression that goes in, and you get a new, bigger substitution and the type of the term you put. So if the term you put in was a variable b, then you look up b inside the context. So the context is the substitution, input substitution a. So you look up b in a, and if it's not there, then you say that's an error, I have an unbound name, because hopefully somewhere outside that was bound by a lambda or a let. But the typing it might not be a type scheme, it might be polymorphic. So you instantiate all the type variables that appear in the type scheme with fresh names for the thing you get back that's bound in the context of the variable B. Okay, done with that? Okay, so let's say the term you put in as an application you want to E2. So a lot of this is kind of noise because you're sort of combining substitutions and you're threading names, supplies, and things. But essentially what we're going to do is first we're going to recur on the first term in E1, which is going to be our function. So here we recur on E1 in the context A. So we get a type T1, which is hopefully a function type for E1. Okay, that's an application. And then here we're going to unify. We apply it to this substitution, but you can just ignore that. So for now, we unify T1 with the function type T2 to B, where T2 is the type that we invert with the thing we apply the function to. So this is how we're gathering local information using unification. So we say that we have an application, so we know that there's functions involved somewhere, and we hope that somewhere that's going to get glued together to other information that's going to give us a global solution. But for now we just collect it and we stick it into the substitution. And we use this unification to assert this equality. Is that clear? Let's go over that in a bit more detail. Lambdas are similar, so if the thing is a lambda, then I'm going to I'm going to return a function type, so b to t1, where I get the type t1 from recurring on the body of the lambda, e1. By doing this, I build up the context with the information of how to get x by giving x this fresh type b. So I generate a fresh type b, and I'm assuming x has type b. I recur and get the type of the body, and then I build a function type out of that type, with b as the function out of the type. So that really closely corresponds to the abstraction book. Except for that, in order to sort of make progress, I had to sort of create this magic, create this BF thinner. And the way I do it is to create a fresh unification variable. So this is like saying, I don't know what B is yet, but the only way I can proceed in the proof tree is to use the abstraction rule. So I'm going to use that, but I'm going to use this unification variable that I don't know anything about. And hopefully by the time you get to the top of the tree, you've learned something about it. last one's let. So this is where we have that generalization rule coming in again. So if we let x be E1 appearing in E2, then first let's infer a type for E1. Okay. So we recur on E1, and then I think you probably see what's going to happen. We're going to extend the context so that x is bound to the type we got T1 for E1, and recur on E2. So we recur on, it's over here, almost. Recur on E2, and the context that we're going to use is here. And somewhere in here we're binding x to T1, which is the thing we inferred for the let back thing, but we generalize it. So you remember on the slide I had let, what was it, f equals something, again f applies to itself. The only reason that was valid was because we did let generalization here. So that I can generalize the type of f and then instantiate it later in the variable rule at two different types. If I didn't use a let, you'd run into the occurs check issue that we had before. So that's why it's useful to separate let from, even though you can sort of encode let using abstraction and application, it's useful to separate it because it gives us a nice place to sit generalization. It gives us sort of a natural place to put generalization in the algorithm. And that's the whole of algorithm W. It's like 100 lines. So that was pretty quick. Does anyone have any questions on the algorithm, first of all? So I think, this is one of my favorite algorithms. I think it's really neat. But you know, you can the technique generalizes. Like say, we have this sort of theory of constraints that comes out of adding unification variables to our type language. But you can add unification variables to any subtype or any type, right? And then you can do constraint solving over it. And algorithm W has, you can do the same kind of thing. This sort of prolog style constraint solving, I guess, with Robinson unification over any type language. And in practice, that's how you implement more interesting programming languages. So you add things like data constructors, and you add things like booleans and strings and all these other things here. And you define the unification code, and then you generalize algorithm W. It's kind of like the building block of this style of language. So that's it.
Does strictness versus laziness have any play at this level?
So it would come into play when we talk about semantics, I guess. I haven't really thought about that.
I was thinking of it because you were talking about ML a lot, which is strict, right?
Right. So you might have a type for lazy things, like you might have funcs explicitly in the language or something. It might come up in the semantic piece because, like I said on the slide, I said we constructed the CPO that was closed on the various things like function construction. You might have more bottoms in your CPO if you were lazy. I don't know, I really thought about it honestly. I just started trying to sort of formalize some of the semantic piece here, but I didn't get through it unfortunately, so not really comfortable going into any detail here, but yeah, it might turn out in the semantic thing.
And is this algorithm strong enough to represent typos?
Wait, typos in the sense of like type wildcards?
Well, like the extension in Haskell where you can leave out stuff to learn more.
So,
where you program using holes.
Oh, right. So there's two that I'm aware of that I would call holes. One is type wildcards, and you can definitely do that. So type wildcard is where you say something like, you set a type annotation for a term, but you don't put all the information. You say, for example, this is a function it's a function, but I'm not going to tell you what the function argument type is, but the return type is int. So you'd say maybe like, the type annotation would be like underscore arrow int. So you can definitely solve that with this method. Every time you see an underscore, you just fill it with a fresh unification variable. And hopefully that gets unified with something sensible. And there's no inconsistencies or whatever.
So if you do that, does that mean that function is polymorphic? Or will it eventually have only one thing in that language?
Well, so it depends, right? So if my function was constant 0, then the algorithm wouldn't learn anything about the wildcard, the unification variable, because the most general type of that is for all a to n. So the algorithm doesn't learn anything basically until it gets to the top, and you still, at the end, you have alpha to ends, and then you let generalize it. Sorry, you generalize that type, and you get the type to be for alpha to end. If it was lambda n goes to n plus 1, then at some point you see the plus, and you get local information in the substitution that says there's an end here, and those get unified. And the monotype you get is end to end, and then you try and generalize that, and you just keep end to end, you can't generalize that. So it depends on the time, it's just, it's kind of like a middle point between not writing an annotation at all and writing a full annotation. In the full annotation case, it might be the wrong annotation if it fails to type check. And the fact can still hold, right? It can still fail to type check. But you may end up pulling off quite a lot.
I did notice when you were looking through it, does this give you any, and I guess I'm talking about implementation too, because it looks like W is strong enough to do it, but probably that's what. Do you get any useful type errors, like I was expecting an in here?
Yeah.
Or would you have to write
So
that in?
it's interesting, like algorithm W can give some, well, it depends on how many things you add on, but it can give some pretty bad error messages. There's actually two algorithms. There's algorithm W and there's algorithm M. And I spoke about bidirectional checking. So you can write a bidirectional algorithm even though you don't need to for the downstream number. And it turns out that algorithm W corresponds to, I think it's right. I think algorithm W corresponds to synthesis and algorithm M corresponds to checking. It said that bidirectionally you have these two type conversions, synthesis and checking. And generally you get better error messages out of that because you have more information. You can sort of, maybe you just augment the term language with type annotations. And in practice, ML you don't have to write any type annotations, what people do, because it's useful for documentation, and then you're going to get better type error messages if you bidirectional check. Yeah, that's kind of like a whole interesting area. There's like a whole bunch of papers written on that.
It felt like there was some space where you have places where you error where the two things don't match up.
Right.
At that point, you know what the types are of what they're expecting.
Yeah, this is like the worst possible error message, right? The slightly better thing is to at least print the two types and say, like, I had a function, but you gave me an int. It's supposed to be a function, you gave me an int. But even then, you can run into, like, because this is very local, right? You said unification happens at the local level. It can error out too soon. You might want to wait until you have, even though you've already failed, you might want to wait until you have more information so you can give the user more context and say, there's a function that appears and this variable is relevant and this variable is relevant.
Sounds like it makes it way harder.
So GHC used to get a bad rap for its error message, but it's getting better and better. Like you'll see things now in the areas where we're unification failed, add function, and you might like to look at type, why has this type? It appears on this line, because it's done extra bits of unification to figure out what's sort of relevant to the error.
Cool.
Did you use this to design the first?
Yeah, this, so if you want to see my blog somewhere, go into the solving constraints generically blog post. This goes over solving, doing kind of like this constraint solving type stuff where we haven't deforested. We've done this explicit split between gathering and solving constraints, but over an arbitrary term language. So this is basically exactly what District used to do based on this. Then I added type custom rank and types and it's bidirectional checker, but the basics are still there.
Thank you, Phil.